So the very last thing we have done on Monday, I think we considered this previous example, probability that absolute value of x is less than 3, given that x is normally distributed with variance 4 and mean -1. And then now let's see if you can solve this problem. So just folded normal, and that means that we take y to equal to the absolute value of z, where z is the standard normal random variable. And what we want to calculate is the mean, the variance, and the density function for y, the distribution function for y, so to speak, right? So let's go ahead and try to do that, see if you can do it, right? So the idea is we take absolute value of a normal. That's why it's called folded normal, because it's like you have this picture of the bell, which you then fold to the positive x-axis. Hey, John. So let me know, guys, when you are ready. So let's go ahead and compute what was the mean of this distribution. So the expected value of y is simply the integral. We know that we don't need to create a new distribution, right? We're able to use the same distribution of z, similar to the discrete random variable case. And so we're just integrating from -infinity to infinity, absolute value of z times the density function for the random variable z. Now, to get rid of the absolute value, I see this is an even function, which means that I can simply multiply by 2 the area from 0 to infinity of z times this expression, yes? And this involves very simple u substitution. The integral of z times e to the minus e squared over 2 is minus e to the minus e squared over 2 and evaluated from 0 to infinity. And the result is root of 2 divided by pi. Make sense? Good. Now, to calculate the variance, I need to calculate the expected value of y squared, right? the expected value of y squared, I don't even need to bother with any calculations, y squared equal to z squared. And the expected value of z squared is the variance of z, which we know to be 1 from previous calculation, right? The variance of the standard normal is simply 1. So that tells us that the variance of y is the expected value of y squared, which is 1, minus the expected value of y squared, which is this number squared, which is 2 over pi. So the answer is 1 minus 2 over pi. Good? So then we need to calculate the density function. So we begin with the cumulative distribution of y. And that's just the probability that capital Y is less than or equal to little y, which is the probability that absolute value of z is less than or equal to y, which is the probability that z is between minus y and y, which is the cumulative distribution evaluated at little y minus the cumulative distribution evaluated at minus y. Again, cumulative distribution, if you remember from Calc 1, it's just the antiderivative function, a very convenient form of the antiderivative. Yeah? So, yes, and so we have this distribution, which we can simplify, right? Since phi of minus y equals 1 minus phi of y. That's by symmetry of this distribution. It's 1 minus phi y. And that will be then when we simplify 2 times phi y minus 1. And when we differentiate with respect to y, we get the density function, which then becomes simply 2 little phi of y. So it's twice the density function at y. Good. One more example from this node set. And that's just possibly to illustrate, it's a very outdated procedure you have in your phone. You can download an application that will calculate the distributions for any normal variable. But what you used to do is you used to always convert it to the standard normal and then consult an integration table, right? For the hell of it, in case you know, at some point you take an in-class exam, right? But not. I will show you how to use. Of course, Mathematica can do it. Anything can do it, really, right? So it's a very outdated skill set, I imagine, right? Mathematica might give you a better list, but I will show you just in a moment what would a z-table look like, right? So this is a z-table, right? So this is calculating the probability of phi equal to those numbers, right? How do you think you're saying? I'm not saying it correctly? I'm sure I'm not, right? This is called, in Russian, it's the letter F, all right? Okay. Right, so in Russian, that's the letter F. And, well, certain people, you know, it doesn't matter, I'm not gonna go there. Right, just people have very strange associations with this letter, at least Americans. Right? I mean, I was told, right? But yes, I was told what it looks to them like, right? So, so this F or phi, right? Russian phi, whatever, right? So it's you have this z-score, and notice that the z-score only is positive, right? So the table, to make it compact, only gives you positive table. That's why. In general, when you have to use the table, you have to convert to phi evaluated at a positive number. So, for example, I want to know what's the probability that my z-score is below, let's say, 1.32 standard deviation. So I go to 1.3, and then I move to the column 2, and here is the probability, right? So, so if my number z here is equal to 1.32. I just look at 1.3 here, and then I move to the third column, and I see my score. Make sense? So yeah, it's so that's how you will solve it. So then let's say if you have x, and it's a normally distributed random variable with mean equal to 3 and variance equal to 9, I want you to calculate. Using the table that I'll display the table in a moment, I want you to try to calculate what is the probability that x is between 2 and 5. Okay, approximate it. So set it up, and then what's the probability that x is bigger than 0, and the probability that absolute value of x minus 3 is bigger than 6. Okay, I will keep the screen on, and then let's say in a few minutes I'll just display the z-score table. I mean, pretty much converted at least to the form where you could look it in the table. Understood? How many of you are taking summer classes, by the way? Which class is interesting? Analysis. Oh, well, guys, too bad, but it's not going to be me who teaches it. What is 702 some statistics class, I'm assuming, right? But you can, if you want to either watch the lectures, I will try also to help you in case you have questions. You can contact me over the summer for analysis, right? I'm not sure if I know what 702. I don't even know the number, so maybe I'm not able to explain it. The video lectures for analysis that I made are posted, of course, you know, years after I enjoy teaching it. So. I saw the name of the guy who is teaching it. He's definitely very smart, very intelligent. I know this guy. Right. So, you know, you might enjoy it very much, but if you have questions with me, I'm happy to explain it my way. You mean regarding the class or regarding analysis, David? All right, let's work through the problem, right? So what do I need to do? I need to change the x to the standard normal. I just need to rescale. So what do? I subtract from x3 and from every other value I subtract 3, and I divide by the square root of 9, by the standard deviation. That's what I do for all of them, yes? So here I have that x is between 2 and 5, which means x minus 3 over 3, which is my z-score, is between 2 minus 3 over 3 and 5 minus 3 over 3. Yeah, I just keep the inequality, subtract 3 everywhere, and then divide by 3 everywhere. And I get that z is between minus 1/3 and 2/3, which, if I'm consulting the table, I have to change into 2 decimal places. So 2/3. So this is basically phi evaluated at 2/3 minus phi evaluated at minus 1/3. Yeah. And again, in the table, I will not see negative numbers. So I have to convert it to make it only phi of positive numbers. For that purpose, I replace this phi by 1 minus phi of 1/3, right? This means the area of the tail below minus 1/3, which is the same as the area of the front of the, if it's like a, what do you call this dinosaur with the long tail and the long head? It's now like the head of this dinosaur. It's equal to, its area of the head of the dinosaur equal to the area of the tail of the dinosaur, and that in terms of phi equals to 1 minus the body, right? So that would be how I get those values. Phi of 1/3 plus phi of 2/3 minus 1. Yes. Now 1/3 is roughly 0.33. 2/3 is 0.6666, which you round up to 0.67. So roughly it's phi of 0.33 plus phi of 0.67 minus 1. And then I go and look at the table. So first I need to find 0.33, I think, right? 0.33, I just go to 0.3, and then I move until I reach to this location. I move to 4th column, yes? And 0.33 then equals to, probability equals to 0.6293, roughly, yeah? And I do the same thing for 0.67. So I go, this is 0.6, and then 7th is somewhere here, in this column, and I see the value. So it's pretty clear what you do. And of course, when you have a computer, you don't bother doing it at all. Right? I even have in my smartphone, I have a program that can calculate for a bunch of distributions. So yeah, so what we get is this is the first score, this is the second score, and I subtract 1, and then I get 0.3779. I then calculate what's probability that x is bigger than 0, and that probability is the same as probability that z is bigger than minus 1, which is 1 minus phi of minus 1, which after I convert is phi of 1 simply. Okay? So it's phi of 1, and the answer then is 0.8413. The final question is we have absolute value of x minus 3 bigger than 6, which means that either x minus 3 is bigger than 6 or x minus 3 is less than minus 6. I then get a probability that z is bigger than 2 and probability z is less than minus 2. So you see, when you convert, if you do have to use the table, you have to end up with probability z less than or equal, it's the same, a positive number, 0 to a positive number. So that makes sense? Good. And then you calculate and you get the number. Good. So let's move on to the next lecture. So why are normal random variables so popular? So the major reason for it is the central limit theorem, which I'm going to explain now. I'm not going to prove the central limit theorem. We need to know moment generating functions, but we will at least here apply this theorem, right? So what the theorem is saying is that if you have random variables x1 all the way to xn, random variables x1 through xn, and those random variables are identically distributed and independently selected of one another, right? So x1 through xn, it's like taking a sample pretty much, right? So and then you see where the distribution is headed, right? So then if n is large, if you have a large sample, no matter what is the original distribution of the random variable x1, x2, x3, no matter what is their original distribution, the summation of those random variables will create a normal distribution. It will be well approximated by a normal distribution, okay? And that's what this theorem is saying. And the normal distribution will have mean equal to the expected value of the sum, and variance equal to the sum of the variances, okay? And by independence, again, we're assuming that each of the x's are independent. By independence, variance can also be written as a sum of the individual variances. Remember, that's not true in general, but that is true when the x's are independent of one another. So the variance of x1 through xn will be simply n times the variance of each individual random variable. And the expected value is n times mu. And so when you want to calculate the probability that x1 all the way to xn, they add up to a number less than b, that amounts to calculating a z-score less than b minus n mu divided by root of n sigma, okay? That's just, all it is this. You think of x1 through xn essentially like a normal distribution, okay? And if it's essentially like a normal distribution, you can make it into a standard normal distribution. Sounds understandable? Let's try a few examples, if so. Yes, I will always, yes, Marcel, I'm sure you are. Believe me, not as confused as I am, or as terribly annoyed. I'm not sure if it's obvious on my expression. You can see this. Thankfully, you cannot smell anything, right? All right, but it's basically, I write those silly lectures, and then I present them, and then I write them, and I present them, and I write them, and I present them, and I write and I present. Anyhow. Yes, well, and that's, by the way, happening anyhow. Of course, what do you think you're getting, right? You're getting A's and and a bunch of money through the government. Everything's great. Super. So here is one question. Re-explain? Yes. Go ahead, Marcel. Tell me, what should I re-explain?
Just what's going on the bottom of the first page. I
okay.
it.
Okay, here we go again, right? So the statement of the central limit theorem, right? The central limit theorem tells us that if we take any random variable, no matter what, it's a continuous random variable or any other random variable, doesn't matter, right? But it has a certain distribution. The distribution of this particular random variable obviously does not have to be normal. But if I take identically distributed random variables, I take many of them. So n is large. I take x1, x2, x3, etc. Right? I take many of them. Then the sum of those random variables will have an approximately normal distribution. And the mean of that distribution will be the expected value of the sum of those random variables. And the variance of this distribution will be the sum of the variances of each of those random variables. They are, again, identically distributed, okay? So yes, it doesn't matter. So for example, imagine that what you're considering is just you are testing a bunch of cars, right? So you have cars, they are produced with basically there is a possibility of faulty cars, right? So then you have a distribution of what's the probability that a car is faulty. That probability does not have to be normal. It might be, maybe the car is made, in a very bad factory, and then the probability is lopsided, right? It's just very highly likely that the car is faulty. But if I basically begin taking samples, independent samples, I just pick random number of cars. And I add up, let's say I add up how many of them basically are faulty, right? Let's say 1, car is faulty, 0 car is not faulty. Let's say we just make it discrete, either faulty, either passes inspection or doesn't pass inspection, let's say, right? So I pick a random sample of such cars, and I pick a big sample. Let's say I pick 1,000 cars like this, right? And then the probability that the probability that those cars, that basically probability that I get n cars or k cars, sorry, that pass the inspection will be roughly, will have roughly a normal distribution. That's what this is saying. I will, by examples below, you might hopefully have a feel for it, okay? So yeah, so that's, and then this last calculation, this very last calculation here, it's only what? It's only converting the normal distribution to the standard normal distribution. Good. Which means what? Which means you have to subtract the mean, and the mean is going to be the expected value of the sum of those variables, and divide by the standard deviation. But the standard deviation is the square root of the variance, which is square root of n times sigma squared. Therefore, you divide by root n times sigma. Good. Good. So, but we see examples below, and again, right, the examples can be complicated, and I certainly have not explained why this is true. But we are just going to see why the normal is useful, because we are assuming this is true, right? If this is true, then you see why you use the normal so many times. So here is one example. So imagine that insurance company has 25,000 policyholders. Okay, so they're basically Geico, let's say, has 25,000 policyholders, and then each of those policyholders might have an accident or some damage to the car, and will file what do you call this? We'll file for we'll file a claim. That's what I think it's called, right? So let's suppose that that the yearly claim that a given policyholder is going to make it's a random variable, right? It can be any number, right? Let's say money varies roughly continuously, right? Like water. So what you have is, on average, imagine it is $320 that will be asked in a year, and the standard deviation is 540. Okay, which means that so you understand, right? So we have, this is our average. We don't know how this is distributed. We just know that the variation from the average is this number squared, right? The square of the variance is this number squared. So what is the probability that this year the total number of claims will exceed $8.3 million? You understand? So each of them will ask for some amount. Some will ask maybe for 0. Clearly, it's not a normal distribution. Do you agree? Because I never heard of people asking to give money to the insurance company. Like they would claim minus something, right? So if it's just how much money they will be claiming, forget about deductible and everything else, right? It's just the amount of money they are asking the insurance to pay. You hear it? He's looking at birds. Yeah. So how do we solve this problem? So here we have that the total sum of claims T is x1 plus all the way to x 25,000, right? So each of those random variables is going to generate the number that the particular policyholder is asking for. Good. So then let's see if you can figure it out before I show the answer, right? So what is your estimation? Do your best to set up this problem and solve it. You understand how you do it, right? So again, the idea is that each policyholder will file a claim independently of any other policyholder. Let's say they don't know each other, okay? And then from that information, you want to estimate what's the probability that over $8.3 million will be asked. Essentially just the setup, guys, right? You don't need to give the final score, just setup. Ready? Yeah. So this is what you do. You simply want to estimate the probability that total is more than 8.3 million. And what do you do? From there, you need to subtract the expected value of t. That's the average, right? Subtract the expected value of t. It's 25,000 times the expected value of x1, which is 320. Yes? And then what do? Then you divide by the standard deviation. It's given here as 540, so I don't need to take the square root here. And multiply on the bottom by root of 25,000. Yes? And you do the same thing to the right-hand side. And so when you simplify everything, you get that it's the probability that z is bigger than 3.51. Good? You understand the idea here is very simply is that no matter how each individual x here is distributed, the sum of them is going to be distributed normally, approximately, right? So we look at what? We look at 1 minus phi of 3.51. So on this table, it's actually it's even, so 3.51, we don't even have it in the table here, right? It's a very low probability. But so the best score we get is maybe, that's the closest we have here in this table. Yeah? So it's actually below, 3.51 is below. So roughly we're going to say 1 minus 0.9990, which is less than, well, which is about 0.001. Okay, so it's actually lower than that, but that's what we are able to see. So another thing that can be demonstrated is that if you have two random variables, x and y, and each of them is normally distributed, so x is normally distributed and y is normally distributed, they have means mu x and mu y, and standard deviations sigma x and sigma y. Then the sum of x and y, x plus y, is also going to be normally distributed. Okay, with mean equal to the sum of those means, but standard deviation equal to the square root of the sum of the squares of the standard deviation. So here is an example of that. So imagine that you have a bridge, and it's the amount of weight that this bridge can withstand in thousands of pounds is random variable w, and it has mean 400 and standard deviation 40, and w is normal, right? So the amount of weight it can withstand in thousands of pounds is w. And then the question is the following, right? So the average weight of a car is it's a random variable. It's a normal random variable with mean equal to 3 and standard deviation equal to 0.3. Okay, the question is to calculate the number of cars, to estimate how many cars we must have on the bridge so that probability of structural damage exceeds 0.1. Okay, so W is basically the weight at which the bridge begins to incur structural damage, and it's normally distributed. So depending on the situation, it might be more, it might be less. Can you figure out at least how to set up this problem? Yes, yes, but just this first the setup is exactly what are we trying to look at, right? What's the z is only when I convert a normal distribution. That's the last step. What distribution do I convert? But you're absolutely correct. 0.9 is eventually a number I need to look at. So just the setup, guys. Everything else is we'll figure it. All right, ready? So would anybody like to tell me before I mention this? So what probability are we interested in? When what happens? No? So the bridge, it has moods, right? Let's say today it doesn't feel like working. Tomorrow it is very strong and hard-working bridge, right? But in general, its moods for how much weight it can withstand is W, and W is told to you that it's normally distributed. Make sense? So and then the cars, the number of cars um, on the road, let's say the number of cars on the road is fixed to be n, right? So let's say all the time it's just fixed to be n, and the cars decide, well, pretty much like certain people, right, whether to be heavy or to be less heavy. Yes, and their average weight is 3,000 pounds with standard deviation 0.3, okay, of each particular car, okay, and T is the total weight. So the total weight of the cars is sometimes heavy, sometimes less heavy, right? So the cars might not, their decision to each individual car might not decide to be heavy or not heavy based on normal distribution. But the sum of the cars, the sum of their weights is roughly normally distributed, assuming that each car on the road is heavy independent of another. Okay? Make sense? No? Good, right? So, so then what are we interested in? We are interested in the probability that the number of weight forced on the bridge is bigger than the number of than the weight that the bridge can withstand, right, without incurring damage. So we're interested in probability that T is bigger than W, or in the probability that T minus W is bigger than 0. Make sense? You understand? I mean, it's like imagine that the bridge is just like a weightlifter, and sometimes there are better days, sometimes there are less. The days are not as good. So W is normally distributed, how much weight it can withstand, and you're told what's the average and what's the standard deviation for W. T is also T is also a normal random variable. Do you agree? Now, the expected value for T, is 3 times n, correct? Because we have n cars, and that's the sum of the expected values of the weight of each car. So it's 3 times n. Good. And minus 400, which is the expected value of minus W. Good. And now what is the variance of T minus W? Because T and W are independent, T minus W, its variance is just variance of T plus variance of minus W, which is the same as variance of W. Yes? And then what's the variance of T? That's just n times the variance of an individual car, which we know to be 0.3 squared. That 0.3 is standard deviation. Okay? Plus the variance of the bridge, it's just 40 squared, the square of the standard deviation. So the variance of T minus W is 0.3 squared times n plus 40 squared, which is 0.09 n plus 1600. Clear? Wonderful. So then the probability that T minus W is bigger than 0 is the probability of T minus W minus the expected value of T minus W divided by the standard deviation of T minus W, which we said the way we figure out standard deviation is you sum the squares of the individual deviations of T and W, and you take the square root. Okay, so that's this number, square root of that number. And we do the same thing here, right? So since we subtracted 3n minus 400, we do the same thing to the 0. Since we divided by this root, we do the same thing to the 0. And we now have this relationship, okay? And this variable on my left on the left is essentially the standard normal distribution by approximation, right? So by approximation, because t is very nearly normal and w is exactly normal, so t minus w is nearly a normal random variable, okay? Which is z bigger than 400 minus 3n over this root, which then is 1 minus minus phi evaluated at this number. That's the probability. If I know n, I just evaluate phi at this number and I have my solution. Yes. Now, what do I want this probability to equal? I want it to be bigger than or equal to 0.1. So I want this to be bigger than or equal. So the probability of damage. This is the probability. This is damage. Right. So the probability of damage is occurred. I want it to be bigger than 0.1. Or I want 1 minus 0.1, this number, right? Be bigger than or equal to this probability. Okay, I just move things around, right? So I have 0.9 has to be a score that's bigger than or equal to phi of z. Okay, and then so I now have to look the inverse score of 0.9. So that means since this is an increasing function, I want to see when is 0. Phi of inverse 0.9 is when is it which scores of z I can look at. So I look into the table and I'm searching for 0.9 on the table. So I'm searching for 0.9 in the table, right? 0.9 somewhere over here, right? So those values are roughly 0.9. Okay, and I see the corresponding z-score. So the corresponding z-score is 1.28. So the number of cars n has to satisfy the following equation, right? I want 400 minus 3n divided by the root to be less than or equal to 1.28, which is the z-score I obtained associated it to 0.9, okay? So I just look to the best of my ability what looks like 0.9 in the table, and that to me looks like the best approximation in the table to 0.9. If you have a computer, you just plug the inverse of this key function at 0.9. And that will give you a score n bigger than or equal to 117. Good. Another question is this, even simpler question. So imagine that you toss a coin 1,000 times. And if the coin is fair, that's part A, how likely are we to get 550 heads or more? So assuming you're tossing a fair coin, how likely are you going to see the outcome of 550 heads or more? The previous problem, guys, you understood, right? I explained well enough. You followed. You understand where I got 1.28 and why this quantity is less than 1.28, because we figured out that 0.9 has to be bigger than phi of z. So I'm searching for all values of z that will produce probability below 0.9. 0.9 or below, I need, right? That means that chance of damage is 10% or more. Yeah. So go ahead, figure out the probability that a coin lands on heads 550 or more times if the coin is fair. Well, wonderful. Let's see what's the answer. So first, again, you see what happens here. So clearly, the number of heads obtained is a binomial distribution, right? But we see in essence that it consists of independent Bernoulli trials, x1 through x1000, where each of them is either 0 or 1, depending on whether we have heads or tails. And because we have each of them is independent and identically distributed, x is roughly normally distributed. Okay, we start with any distribution, doesn't have to be binomial. Any distribution, if I have a big sample, right? So the samples, the sum of the samples is going to be normally distributed. So then, what's the expected value of this x? It's going to be 500, naturally, right? 500. You expected it because it's half of them should be heads, also by calculation. Now, what's the variance? By independence, the variance is simply the sum of the variances of each x, which means it's 1000 times variance of x1. Variance of x1 equals to a quarter. Yes? Variance of x1 equals to a quarter. It would be 1/2 minus 1/2 squared, because the expected value of x1 squared is still 1/2. Yeah? So it's 1/2 minus 1/2 squared, which is 1/4. So we have 250 is my variance for x. And so the probability that x is bigger than or equal to 550, I simply convert it to be standard normal. I subtract 500, divide by the square root of 200, and I obtain roughly a z-score of 3.16, as Isabella just said in the text. Okay, I just simplify it. It's z bigger than or equal to 3.16, and that can be calculated from the table by asking for what's 1 minus phi of 3.16. Makes sense why 1, right? Because the table only tells you the values of phi at different positive numbers. Okay, so I have to, if I look through the table, I have to make it positive, right, and whatnot. And so we have 1 minus it, which is 8 out of 10,000. Yes, it's 8 out of 10,000. So which seems very unlikely. Yes. So the second question is the following, right? So you don't know what if the coin is fair or not, but you tossed it 1,000 times, and 550 of those times were heads. What are you automatically convinced? So this is a very small probability, right? Are you convinced the coin is not fair? No. That's an interesting question, right? I mean, is it evidence to be convinced that the coin is not fair? And we will talk about it when we talk about beta distributions more so. But here is an example to consider, right? So I would imagine that in certain situations you would think, well, this is a small number. I don't believe this coin is fair. But before you make your judgment, consider this example. I will at least say the example. Maybe we'll discuss it on Monday, right? So that's what I was writing right before. It's kind of a few moments. I barely finished, right? So imagine that there is a teacher, and the teacher is working at an inner city school called Children Are My Sunshine. And in the school, you have 101 pupils. 100 of those pupils are wonderful darlings, but the 101st is Dennis the Menace. So after a day of work, the teacher sits to rest in her favorite chair, only to discover that there are pin boards on this chair. So she's very upset at this prank. She goes to the principal and demands the immediate expulsion of Dennis the Menace. She's convinced that that's his fault. Okay, and the reason she's convinced it's his fault, let's say this is the reason, right? They say she's absolutely certain that the prank must have been the handiwork of one of her students. It had to be one of the 101 students that she has in her class. And she is convinced with the following, right? So if Dennis were innocent, the likelihood that this would have happened is 10 to the minus 3, supposedly a small probability. In other words, it couldn't be, she's saying, well, it couldn't be anything else, because if he were innocent, it will be very unlikely. I'm not sure, maybe you don't believe this is unlikely enough, but let's say for our purposes, that's quite unlikely. Yeah, 10 to the minus 3 is rather unlikely. So assuming that assuming that the premises I and double I are, taken at face value, assuming that this is true, that the principal agrees with those premises, what should be the actions? Should there be, what should the principal do? Should the principal expel Dennis the Menace or not expel Dennis the Menace? That's the question. You understand? I mean, and that's the evidence given, right? I understand. I'm not claiming that there is just a complete calculational argument that you can go just from here. Just is the evidence enough to convict? Okay, so it's given, it's taken to be true, proved, or believed by everyone that this crime is the handiwork of one single person, and that had to be one of the 101 possible suspects. And if Dennis were innocent, the probability would have been 10 to the minus 3 that such a thing happens, right? If you were innocent, the probability that there will be nails on the teacher's chair is 10 to the minus 3. So at this point, the class is officially over. Think about it. I will add a few things to the notes, and then I will scan it, and we will continue with this on. We will continue on Monday. If you yes, in the textbook it's roughly chapter 5. Although I don't go exactly by the textbook, I switch a few things here, right? Right. So if you have questions or anything else, you can stay longer. I will pause the video at this moment.